Close your eyes and imagine a future where the sky has grown stranger, storms longer and crueler, summers that do not end, or the fragile web we call ecosystems failing in a cascade. We prepare tonight not to dwell on doom, but to think quietly and clearly about options humankind has proposed across decades of science and imagination, the practical and the poetic paths beyond a suddenly hostile surface. There are three clusters of responses that have real technical literature behind them: staying below the ground, leaving for other worlds, or living in space itself. Each path carries its own engineering demands, timelines, and moral choices. Let us walk slowly through what we know. First, the idea of living under the surface, building cities underground, is older than modern space programs. People have sheltered below ground for millennia. Cappadocia's rock towns, wartime bunkers, Cold War complexes. Today, underground living is not just about hiding. It's about harnessing the stable temperatures, natural shielding from radiation, and the protection from severe surface weather that deep subsoils provide. Modern engineers and architects have proposed multi-level subterranean habitats with ventilated streets, vertical farms in bioreactors, and artificial sunlight delivered by fiber optics or LED systems. Science has already tested parts of this puzzle. Growing food below ground in controlled environments is practical at small and medium scale. Indoor vertical farms and mushroom and root crop production show how plants can thrive without natural sun, using LED spectra tuned to photosynthesis. Projects like Growing Underground in London demonstrate urban agriculture in disused underground spaces, proving that food systems can move below the surface in a pinch. Scientists also study human health and biology in deep underground labs, where isolation, low background radiation, and different microbial communities provide insight into long-term living below grade. These studies reveal both promise and caution. Subterranean habitats can provide thermal stability and protection, but they require robust, redundant life support and psychological design to prevent isolation stress. We also have decades of hard lessons about closed living systems from large experiments on Earth. The most famous demonstration is Biosphere 2, the Arizona enclosed ecosystem built to test whether a materially closed biosphere could support human life and agricultural production. The project showed that many parts of a closed ecosystem can be engineered. Agriculture produced much of the crew's diet, and the structure could be sealed and monitored. But it also revealed surprising chemical and ecological feedbacks, carbon cycles, oxygen drawdown, and species die-offs that challenged simple expectations. Biosphere 2 taught engineers how to design airtight seals, manage waste recycling, and produce food in a constrained area. It also taught psychologists and designers about group dynamics in closed habitats. In short, underground cities are technically feasible in principle, and many of the needed technologies, controlled environment agriculture, efficient heat and water recirculation, and microbial waste processing and structural earthwork already exist. But scaling these systems to sustain millions is a different order of challenge. Resource flows, energy supply, maintenance logistics, and long-term genetic and microbial stability become central concerns. If we consider leaving Earth altogether, the nearest and most discussed target is Mars, with the Moon as an intermediate stepping stone. Mars appeals because it is a solid world with gravity, about 0.38 g, known resources including polar and subsurface ice, and a day length similar to Earth. Over the last 2 decades, agencies and companies have mapped landing sites, tested entry landing precision, and begun demonstrations of critical subsystems, in situ resource utilization, or ISRU, for oxygen and propellant, habitat design studies, and crop experiments in simulated Martian regolith. SpaceX has been the most public proponent of rapid Mars colonization, building the Starship vehicle to carry large cargo and crews. Company leaders have published timelines and roadmaps for cargo flights followed by crewed missions to deliver habitats, ISRU plants, and life support units. Government programs such as Artemis/Lunar Gateway architecture also pursue a stepwise approach. Test and learn on the Moon, build logistics and rendezvous capability, and then apply these lessons to Mars. These plans are ambitious and advancing. Hardware demonstrations, orbital refueling concepts, and ISRU prototypes are in active testing today. Yet even optimists emphasize that establishing a self-sustaining human presence on Mars would take decades and massive industrial infrastructure involving hundreds to thousands of launches and a sustained commitment of international and private capital.
There is also the longer, theoretical idea of terraforming, altering a planet's atmosphere and climate so it becomes more Earth-like. Serious scientific reviews treat terraforming as a speculative, centuries to millennia scale enterprise. Agencies such as the European Space Agency and academic teams have modeled scenarios, from releasing greenhouse gases to thicken an atmosphere, to redirecting cometary bodies to deliver volatiles, and concluded that while the physics does not violate fundamental laws, the energy and material scales involved are enormous and ethically fraught. Terraforming also raises legal, ethical, and planetary protection questions. Should we irrevocably alter another world's environment, possibly destroying any native microlife we do not yet know? For reasons of cost, time, and ethics, terraforming is not a near-term escape hatch. It is imagined as a multi-century dream at best. Between digging and colonizing lies a third option that has captured imaginations since Gerard K. O'Neill's work in the 1970s. Free-flying space habitats, Stanford Tori, O'Neill cylinders, and other rotating megastructures that create artificial gravity by rotation, anchored in Earth orbit, at Lagrange points, or in solar orbit. The attraction of these designs is pragmatic. Build habitats in space using materials from the Moon or asteroids, use large mirrors or solar arrays for power, and create vast habitable land area per unit mass. Technical studies, NASA's 1975-77 space settlement studies, subsequent analyses, show it is physically possible to design such habitats, and some modern research updates cost and materials assumptions using current launch prices and in-space manufacturing ideas. However, the upfront industrial scale is unprecedented. Historical cost estimates for prototypes and first colonies range from hundreds of billions to trillions of dollars in constant dollars, and require mature space mining, in-space assembly, and robotics industries to reach realistic economics. That said, if humanity were committed to off-Earth living on a civilization scale, orbital habitats offer advantages: continuous solar flux for power, easy access to microgravity manufacturing, and modular growth potential without irrevocably altering another planet. Recent proposals also emphasize incrementalism, starting with smaller inflatable modules, closed-loop life support test beds, and growing to larger rotating structures as in-space manufacturing matures. All three options, underground, Mars-Moon colonies, and orbital habitats, share a common engineering core: life support. We already operate sustained life support in low Earth orbit on the International Space Station. The ISS provides oxygen generation, CO2 removal, water reclamation, waste management, and small-scale food production systems. Plant growth modules like veggie and the advanced plant habitat. But the ISS is not built to support hundreds or thousands of people indefinitely and is nearing the end of its operational life. NASA and partners are actively planning transition strategies for post-ISS research platforms and commercial low Earth orbit habitats. The lessons of the ISS tell us that closed-loop engineering is possible, but scale, redundancy, and maintenance cost explode as habitats grow. Research into bioregenerative life support systems, or BLSS, combining physicochemical recycling with plants and microbes to regenerate air, water, and food, is mature in concept, but still in prototype form for sustained, large-scale operation. Recent NASA technical reviews and academic surveys summarize progress in CO2 scrubbing, urine recycling, crop yields in microgravity, and the psychological care of crews in closed environments. These technologies point the way, but they are not yet plug-and-play for a million-person underground city or O'Neill colony. We should also factor in radiation and health. Deep underground, you are naturally shielded from cosmic rays and solar particle events. This is a clear advantage compared to living on the surface if the magnetosphere fails or ozone collapses. On Mars and the Moon, radiation is a major hazard. Without an atmosphere or magnetosphere like Earth's, cosmic radiation and solar storms pose both short-term and long-term cancer risk. Shielding strategies for off-Earth habitats include burying habitats below regolith on Mars or the Moon, using water or hydrogen-rich materials as shields, and placing sensitive areas behind mass. Space habitats in high orbit or at Lagrange points require thick structural shielding too, or materials engineered to attenuate high-energy particles. Mitigating radiation is possible, but it means mass, lots of it, and that mass must be launched or mined in space, which again stresses the logistics chain. Another crucial axis is food and energy. Underground cities require continuous energy inputs for lighting, ventilation, and pumps. They need distributed agriculture or high-efficiency vertical farms. Space and lunar habitats require dependable power. Solar is abundant in space, but energy storage, radiators, and thermal control are engineering constraints. On Mars, dust storms can slash surface solar harvest for months. Nuclear power or hybrid systems are likely necessary. In every option, scaling up food production from greenhouse plots or veggie-style modules to city-scale agriculture demands substantial area, lighting, and nutrient cycles. NASA and space agriculture research show promising crops and techniques: hydroponics, aeroponics, microbes for nitrogen cycling. But yields, labor needs, and reliability in exotic gravitational and radiation environments are still active research problems. Then there is cost, time, and governance. The cost of mass-lifting materials to orbit has fallen dramatically with reusability, but it remains expensive. Building habitats at planetary scales demands a long economic and political commitment. Historically, concentrated public investment, wars, national programs, global emergencies, accelerates infrastructure construction, but it also concentrates control. If Earth became uninhabitable, who would organize the migration? Would the wealthy flee first, or would coordinated global governance allocate seats by need? Ethical questions cry out for answers. Who gets to survive and on what terms? Designing any resilient plan requires not just engineering, but just allocations, international cooperation, and legal frameworks for space resources and habitation. The Outer Space Treaty and other frameworks will be tested and likely revised as humans attempt to settle the Moon or Mars at scale. So what is best for humanity given the facts? The evidence supports a layered, redundant strategy rather than a single best answer. First and foremost, preventative action on Earth remains the highest return investment. Avoiding uninhabitability by aggressive climate mitigation, nuclear risk reduction, and biodiversity protection costs far less in human and economic terms than mass evacuation. But when prevention fails, or for insurance against extreme tail risks, the practical near-term refuge is subterranean and hardened surface infrastructure combined with distributed microgrids and local closed-loop food systems. These are the cheapest, fastest, and most technically mature options for protecting large populations in the short term. They use mostly terrestrial engineering skills and supply chains, and they can be scaled incrementally. For medium-term survival over decades, the Moon and near-Earth infrastructure are likely stepping stones. Lunar bases and cislunar habitats let us test long-duration life support, ISRU, water ice extraction, oxygen production, and economies of scale in logistics. They reduce the distance problem. Resupply and communication are far faster than to Mars. Programs like Artemis and the Lunar Gateway, combined with private vehicles like Starship that aim to lower launch cost and lift large payloads, create a pathway to build the industrial base necessary for larger projects. These are practical, test-bed approaches that de-risk Mars and orbital habitats.
For true multi-century resilience, a diversified portfolio of habitats is wise. Distributed underground refuges on Earth, lunar and cislunar colonies to preserve industry and knowledge, early Martian outposts that test closed-loop systems and ISRU, and long-term research into orbital habitats and in-space manufacturing. Orbital habitats, while expensive, offer enormous potential when coupled with asteroid and lunar resources for building mass cheaply in space and solar power collection at full efficiency. Over centuries, such habitats could outgrow planetary constraints. That future requires mature robotics, asteroid mining, and an interplanetary economy. Not impossible, but not near-term either. Finally, the moral choice. If we choose a survival path, it must be inclusive, science-led, and oriented toward restoring Earth. Off-Earth living should not become an escape for the few while the many suffer. The best long-term plan is a resilient strategy that prioritizes Earth's restoration while building the technical, legal, and ethical frameworks that would allow humanity to survive and flourish in multiple environments. Practically, that means accelerating decarbonization and nuclear safety now, funding urban resilience and underground refugia, investing in lunar testbeds and ISRU, scaling bioregenerative life support research, building on Biosphere 2 lessons, supporting agricultural and medical resiliency research, and continuing to reduce launch costs and develop in-space manufacturing so that orbital habitats can become economically achievable in the next century. As you drift now away from these technical possibilities, imagine a future that is not either-or, but both and. People tending gardens in sunlit underground atria, engineers on the moon testing the first full-scale oxygen plant, children born under the slow dusk of an orbital cylinder learning songs from those who remained on Earth. The practical wisdom implied by the evidence is steady. The path to survival is redundancy built on justice, and technology alone cannot substitute for cooperation. If we must face a future where the surface grows unkind, let our response be measured, humane, and rooted in the knowledge that the most powerful technology is our shared willingness to protect one another and the pale blue world that remains the best home we have ever known.
This is not a story of fear, but of wonder, of resilience,
and of the endless curiosity that defines us as human beings. You're listening to When Earth Becomes Uninhabitable, Humanity's Next Home. A slow, meditative exploration of what could happen and what we might become when our home can no longer protect us. Breathe deeply. Imagine Earth spinning silently in the void, blue, fragile, and luminous, a jewel of life adrift in the black sea of space. For billions of years, it has sheltered us, nourished us, and held our dreams. But what if one day it can no longer do that? What if the skies turned red? If the oceans rose, swallowing cities? Or if war left the surface scarred and silent? What if the very air we breathe, the gentle wind on your skin, became toxic? Would we find a new home? Or would we fade into the pages of cosmic history, a species that once reached for the stars but could not escape its own fire? Tonight we begin by looking not to the stars but to ourselves, to the signs already written on our world. Climate scientists warn that by the end of this century, Earth's temperature could rise by more than 3 degrees Celsius. That may sound small, but it's enough to redraw coastlines, melt polar caps, and unleash droughts and storms that could make entire regions unlivable. Already, we see cities battling heat waves and floods, forests burn where they once grew green, and beneath it all, a quiet question stirs in the back of humanity's collective mind. If not here, then where? Let's travel back to the roots of that question. In 1972, NASA launched the first blue marble photograph, a full image of Earth from space. For the first time, we saw ourselves as one. No borders, no divisions, just a single living world. But even then, visionaries like Carl Sagan and Gerard K. O'Neill were asking, what happens when this blue marble can no longer sustain us? O'Neill, a physicist at Princeton, proposed something extraordinary: vast space habitats orbiting Earth. He imagined cities spinning in the void, giant cylinders where artificial gravity would keep people grounded, and sunlight reflected by mirrors would nurture green fields inside the walls of space. That was one dream. Others looked to the planets, to Mars with its silent red deserts, and to the icy moons of Jupiter and Saturn. If we could not stay on Earth, perhaps we could make another world like it. But before we can imagine leaving, we must understand why we might have to. The threats are not all distant. Humanity today faces a convergence of crises: climate change, nuclear proliferation, overpopulation, and ecological collapse. Each of these could, in its own way, make parts of Earth uninhabitable within a few centuries or less. Consider a nuclear winter, a global catastrophe that could follow even a limited atomic war. Models from the National Center for Atmospheric Research suggest that just 100 detonations, less than 1% of the global arsenal, could send soot and smoke into the stratosphere, blocking sunlight and lowering global temperatures by several degrees Celsius. Crops would fail, ecosystems would collapse, and the Earth that once gave us life could turn cold, dark, and silent. Others fear something slower but equally inevitable: the exhaustion of our planet's resources. As our population grows, the demand for energy, metals, and fresh water stretches what the Earth can provide. By 2050, we may need twice as much energy as we use today, but our methods of producing it still poison the skies and seas. If left unchecked, our own progress could destroy the foundation it stands upon. So the question arises, should humanity wait for collapse or prepare for renewal elsewhere? Over the next 6 parts, we'll explore that question in depth. We'll visit the corridors of research stations, the red plains of Mars, the hidden worlds beneath the Earth, and the quiet vacuum of orbit. We'll see what science has already built and what dreams are still waiting. But before we look outward, we must look at what we still have here. Even in the face of disaster, Earth remains the most hospitable planet we know. It has breathable air, liquid water, and a magnetic field that protects us from the radiation of space. To replicate those 3 things anywhere else is an engineering challenge beyond anything we've achieved. That's why many scientists now say the best way to save humanity may still be to save Earth.
Yet we cannot ignore the reality that change may come faster than repair. As glaciers melt and sea levels rise, billions could be displaced. Deserts will expand, fresh water may vanish from whole regions, and even if humanity survives, life as we know it may not. So we prepare. Quietly in laboratories and space agencies around the world, humanity's backup plans are taking shape. In the deserts of Texas and Kazakhstan, rockets rise, carrying the seeds of our survival into the void. The International Space Station has been orbiting Earth since 1998, a fragile home among the stars. It's small, cramped, and temporary, but it proves something crucial. Humans can live in space, breathe there, work there, adapt there. And that realization, though small, may be the key to everything that follows. As you listen, imagine drifting beside that station, floating weightless, looking down at Earth below. You can see the thin blue line of its atmosphere wrapping it like a fragile veil. It's beautiful. But from up here, you can also see the fires, the storms, and the scars. If you close your eyes now, imagine that veil thinning. Imagine that one day the only way to see Earth's sunrise will be from orbit. Would you stay behind or join those who leave? In the next part, we'll travel beyond Earth's gravity into the dream of the orbital city. We'll explore the technology, science, and imagination behind building homes in space, vast floating worlds where life could continue long after Earth falls silent. As we drift farther from Earth, the blue sphere grows smaller, fading behind the glow of the station's solar panels. The silence is immense. Only the faint whisper of air circulating through the cabin reminds us that we are still alive. Out here, life is not a birthright, it is an achievement. Every breath is engineered, every drop of water recycled, every sunrise seen through a window of tempered glass. Humanity's first step beyond its cradle is not a giant leap, but a delicate balancing act between life and vacuum. This is the world of orbital living, cities in the sky, the dream of a civilization suspended between worlds, untouched by the chaos below. To imagine it, we return to a time when this idea first emerged, not from science fiction, but from physics. In the 1970s, as environmental fears and overpopulation haunted the imagination, a Princeton physicist named Gerard K. O'Neill posed a radical question to his students. Is the surface of a planet really the best place for an expanding technological civilization? The answer, to his surprise, and soon to NASA's fascination, was no.
O'Neill and his team envisioned massive rotating space habitats, immense cylinders, miles long, spinning slowly to create artificial gravity through centrifugal force. Inside these structures, entire ecosystems could exist: forests, rivers, fields of crops, even small towns. The light of the sun would be redirected into them using vast mirrors, creating a perpetual artificial day. Birds would fly under curved skies, clouds would drift along the inner walls, and from one end to another, the horizon itself would bend upward. These O'Neill cylinders became an icon of 20th century futurism, a poetic vision of space not as an empty void, but as a second Eden built by human hands. This concept was more than fantasy. NASA's 1975 summer study at Ames Research Center brought together scientists, engineers, and artists to design practical orbital habitats. Their studies showed that such structures could, in theory, house tens of thousands of people, powered by sunlight, sustained by closed ecological systems, and built from materials mined from the moon or near-Earth asteroids. The dream was technically possible, but economically far beyond reach. The 1970s world, struggling with oil crises and Cold War tension, was not ready to build a second home for humanity. But the blueprint was drawn, and it has never been forgotten.
Today, half a century later, the technology that once seemed like fiction is quietly taking shape. SpaceX's Starship, Blue Origin's New Glenn, and NASA's Orion spacecraft mark a new era of reusable, heavy-lift rockets capable of carrying the massive payloads needed to build in orbit. 3D printing in microgravity, tested aboard the International Space Station, can already manufacture tools and structural components without relying on Earth's gravity. Companies like Axiom Space and Orbital Assembly Corporation are planning the first commercial space stations, precursors perhaps to O'Neill's dream. And at the heart of these projects lies a single purpose: to prove that humans can live, work, and grow beyond the surface of their birth. Imagine for a moment such a place. A vast cylindrical world slowly rotating in the dark, its mirrored panels glinting in sunlight. Inside, there is no up or down, only inward and outward, curved horizons rising above you. As the habitat turns, you feel gravity pressing gently beneath your feet, though you are 100,000 miles from any planet. Through the window, Earth glows softly in the distance, blue and perfect, a memory of home. The air smells faintly of metal and vegetation. You walk past a hydroponic field where rows of green leaves shimmer under artificial sunlight, each drop of water carefully recycled, each breath of oxygen measured and renewed. This is life sustained by mathematics, by chemistry, by the fragile miracle of human ingenuity. To build such a city, humanity would need to master closed-loop life support systems, an area of research already decades in progress. NASA's Environmental Control and Life Support System, aboard the International Space Station, recycles about 90% of all water used by astronauts. Carbon dioxide is scrubbed from the air, oxygen is generated through electrolysis, and waste is carefully processed to reduce loss. Yet the system remains imperfect. Long-term orbital living will require complete recycling, what scientists call a bioregenerative system, where plants, algae, and microbes create a balanced miniature biosphere. Experiments like Russia's BIOS-3 and NASA's upcoming Lunar Gateway studies are inching toward this goal, where humans and nature coexist in perfect feedback. Power, too, is within reach. Solar panels are already the backbone of orbital technology, and future designs may extend to space-based solar farms, massive arrays capturing the sun's energy and beaming it back to Earth through microwave transmission. The same systems could easily power orbital cities, offering an endless source of clean energy. Gravity, on the other hand, remains an engineering puzzle. Artificial gravity through rotation works in theory, but scaling it to comfortable, natural motion requires habitats miles wide. Small-scale versions cause disorienting Coriolis effects, where every movement feels subtly twisted, like walking in a dream. These are not small challenges, but they are not impossibilities either. They are problems waiting for patience, creativity, and time. And what about radiation, the invisible sea that bathes all life beyond Earth's atmosphere? Cosmic rays and solar particles are lethal to unprotected humans. The International Space Station orbits within Earth's magnetic field, but long-term habitats farther out would not have that shield. Scientists propose several solutions: thick walls made of lunar regolith or asteroid material, layers of water and hydrogen-rich polymers to absorb radiation, or even electromagnetic shielding, an artificial magnetic bubble around the station. These ideas, once science fiction, are now under active study at ESA, NASA, and private research centers. In 2023, the European Space Agency began testing radiation bricks, modular shielding made from materials derived from space dust. The dream of safe, permanent life in orbit grows closer with each experiment.
But beyond technology lies philosophy. To live in space means to redefine what it means to be human. Imagine children born aboard an orbital city, their first steps taken not on soil, but on metal floors beneath artificial skies. Their sense of home would not be a planet, but a place that moves, spins, and hums with machinery. They would measure time not by sunrise and sunset, but by the turning of mirrors and the rhythm of maintenance cycles. And yet, perhaps they would love their world just as deeply as we love ours. Perhaps they would look down at Earth not with longing, but with gratitude, the way one might remember a childhood home, far away but forever part of their heart. If Earth becomes uninhabitable, such orbital habitats could serve as lifeboats, sanctuaries for knowledge, culture, and species. A network of self-sustaining stations orbiting Earth, Mars, or the Moon could preserve human civilization even if the planet below falls silent. NASA's Artemis program aims to return humans to the Moon by the late 2020s, establishing a permanent outpost. That lunar base could be the first stepping stone, both as a construction site and as a home for larger orbital colonies. The Moon's weak gravity makes it ideal for launching construction materials, while its surface holds abundant aluminum, silicon, and oxygen, the building blocks of habitats and solar panels. In essence, the Moon could become humanity's first industrial world, the forge for our future homes in the sky. Still, as wondrous as it sounds, orbital living comes with profound psychological and ethical questions. Can humans truly thrive without Earth's natural rhythms? The International Space Station has taught us that isolation, confinement, and the absence of nature can deeply affect mental health. Even in the vast beauty of space, loneliness is a silent companion. Engineers can design systems for oxygen, water, and gravity, but what of purpose, connection, and belonging? These too must be engineered, not with machines, but with meaning. To address this,
Some futurists propose orbital habitats not as cold machines, but as living worlds. Spaces designed with gardens, lakes, and even seasons simulated through changing light cycles. Artificial ecosystems where people can walk barefoot on soft soil, hear birdsong, and watch trees grow even as they drift thousands of miles above the Earth. This idea merges architecture, psychology, and art into a single vision, not survival, but continuation, not escape, but renewal. The first prototypes may come sooner than we think. Axiom Space plans to launch its first commercial module in the late 2020s, which will later detach to form a new independent station. Orbital Assembly Corporation's Voyager station aims to build the first rotating hotel with simulated gravity using centrifugal force. These are small beginnings, but every great civilization starts with one structure, one spark of belief that it can be done. Perhaps one day, centuries from now, vast rings of light will encircle the Earth, shining softly like halos in the night sky, the homes of those who refuse to surrender to extinction. Out here, time loses its shape. Days are marked not by the sun, but by orbits, by the slow drift of continents below. The Earth still shines, but no longer holds us. We have built our cities above it, fragile, glittering islands in the void. And from their windows, we look down at the world that made us, wondering if it is healing or if we left it too soon. In the next part, we will journey inward, not outward. We will descend beneath the surface of our planet into the idea of underground civilizations, vast subterranean cities built to withstand fire, radiation, and time. If we cannot escape into the stars, perhaps we can survive within the bones of the Earth itself.
Beneath your feet lies another world, silent, ancient, and largely unexplored. It is a world carved by water, shaped by molten rock, and hidden from sunlight since the dawn of time. For most of human history, the underground has symbolized fear, death, and the unknown. But as the surface of our planet grows unstable, threatened by war, climate collapse, or radiation, this once feared realm may become our final refuge. If the sky above becomes toxic, if storms grow endless, if sunlight turns hostile, the future of humanity might not be in the stars, but in the stone. Deep within the Earth, where temperature and pressure remain constant, life could endure long after the surface becomes uninhabitable. The idea of living underground is not new. Throughout history, civilizations have turned to the Earth for safety. Thousands of years ago, during times of invasion and war, ancient people sought shelter in Derinkayu, a vast underground city beneath the plains of Cappadocia in modern-day Turkey. Carved from volcanic rock, Derinkayu could house nearly 20,000 people, complete with ventilation shafts, wells, storage rooms, stables, and even chapels. Narrow tunnels could be sealed with giant rolling stone doors, protecting its residents from invaders above. It was, in every sense, a functioning underground metropolis, a self-contained world beneath the Earth's skin. The underground has always been humanity's instinctive shield. During World War II, Londoners took shelter in the tube tunnels, while Soviet engineers designed elaborate nuclear bunkers like the sprawling complex beneath Moscow's Tagansky district. In Beijing, the underground city, a Cold War relic, once spanned nearly 85 square kilometers, designed to protect millions of citizens from nuclear attack. What began as emergency protection evolved into an architectural philosophy. The deeper we go, the safer we are. But can we truly live there?
not for days, but for generations. To understand this, we turn to modern science and engineering. In recent decades, urban planners and architects have begun exploring subterranean megastructures, vast self-sustaining habitats beneath the surface. Cities like Montreal, Helsinki, and Singapore have already built large underground networks that connect malls, transportation systems, and workplaces. Helsinki, in particular, is a modern model of subterranean planning. Its underground city includes data centers, swimming halls, churches, and even a hockey rink, all carved into granite. The city's rock shelters maintain a stable temperature year-round, reducing energy needs and offering natural protection from extreme weather and radiation. If we extend this idea into the far future, we can imagine entire human civilizations relocated below ground. Using tunneling technology like Elon Musk's The Boring Company's machines or the giant TBMs, tunnel boring machines, used in projects like Gotthard Base Tunnel in Switzerland, we could dig vast networks capable of supporting millions. Unlike the surface, the underground offers consistent temperatures, typically between 10 degrees Celsius and 20 degrees Celsius, depending on depth and latitude, ideal for climate control. Shielded from radiation, storms, and pollutants, these subterranean cities could maintain stable environments indefinitely. Energy would be critical, and science already provides several possibilities. Geothermal energy, drawn directly from the Earth's heat, could power underground habitats sustainably. Countries like Iceland already harness geothermal power on a large scale, proving its reliability. Combined with advanced battery storage and solar energy harvested on the surface, future underground cities could remain self-sufficient for centuries. Fusion energy, once achieved, would make this system nearly limitless. The greatest challenge, however, isn't energy, it's life support and psychology. Humans evolved under sunlight. Our circadian rhythms depend on it. Without access to daylight, the body's internal clock falters. Sleep cycles, hormone levels, and even emotional stability can collapse. To overcome this, engineers have experimented with artificial skylights, LED systems that mimic the natural hues and rhythms of sunlight. Japan's Denjisha lighting project and NASA's own light therapy experiments aboard the ISS demonstrate that with precise wavelength control, we can simulate dawn and dusk with remarkable realism. In future underground environments, artificial days could be programmed, complete with sunrise tones in the morning, midday brightness, and soft amber evenings. Then there is the question of space and spirit. Humans need openness, a sense of horizon, something the underground does not naturally offer. This is where architecture becomes art. Future subterranean designers propose cathedral-like caverns, vast open chambers filled with vertical gardens and reflective surfaces to simulate depth and sky. Imagine a massive underground atrium lit by bioluminescent walls and fiber-optic stars that glow softly against the stone ceiling. Streams of recycled water run through carved channels, powering turbines and nourishing underground vegetation. In these spaces, the boundary between survival and beauty dissolves.
And nature, surprisingly, can adapt with us. Researchers have studied the growth of plants under LED and artificial light conditions, and the results are astonishing. Crops like lettuce, wheat, and even tomatoes can thrive in fully enclosed hydroponic systems. No soil, no sunlight, just light, water, and nutrients. The Eden ISS project in Antarctica and NASA's Veggie experiment aboard the ISS have already demonstrated this. In the ice of Antarctica, where outside temperatures drop to -60 degrees Celsius, scientists are growing food year-round using controlled light environments. This same technology could feed entire underground populations. Water, too, can be reclaimed. Condensation from air, purified groundwater, and closed-loop recycling systems could sustain communities for generations. Combined with advanced waste management and air filtration, an underground biosphere could, in theory, achieve total sustainability, a sealed ecological circuit mirroring the one we are already testing in orbit. But even with technology, a question lingers. Would humanity thrive in the dark? Underground living would demand not only physical adaptation, but psychological evolution. The absence of sunlight, open sky, and seasonal variation could lead to a phenomenon known as cabin fever, disconnection, anxiety, and loss of time perception. To counter this, architects and psychologists envision dynamic architecture, living environments that change and evolve, mimicking weather patterns and landscapes. Artificial rain, scent diffusers that mimic forests and oceans, and even projected wildlife holograms could help preserve mental well-being. Some futurists suggest using virtual reality environments to simulate nature, vast digital parks where inhabitants can walk through forests or sit beside virtual oceans that feel almost real. Yet in a deeper sense, the underground represents something more profound, a return to our origins. Life itself began in the shadows, in the ocean's depths, protected from the sun's radiation. Early mammals survived cataclysmic asteroid impacts by burrowing underground, while dinosaurs perished above. The Earth's crust, in a strange way, has always been the planet's memory, preserving fossils, civilizations, and secrets. To live within it would be to merge with the planet itself, to become one with the ancient rhythms of stone and time. Modern research supports the potential for long-term underground habitation. The U.S. Department of Energy's Subterra initiative, the European Union's Deep City project, and private firms in Japan and Finland are studying the feasibility of underground infrastructure, not just as emergency shelters, but as extensions of urban growth. Singapore, limited by land space, has already built underground data centers, transport tunnels, and military facilities, all operating efficiently beneath the surface. These are the prototypes of future subterranean worlds. And if we think beyond Earth, this concept takes on cosmic importance. Planets like Mars, with its thin atmosphere and high radiation, are not suitable for surface living, but beneath its crust, in lava tubes and caverns carved by ancient volcanic flows, we might find safety. In fact, NASA and ESA missions have already identified massive lava tubes on Mars and the Moon, large enough to house entire colonies. These natural caves, shielded from cosmic rays and temperature extremes, are now considered the best locations for early Martian habitats. What we learn from building underground on Earth could one day save us on other worlds. Imagine this: a city miles beneath the Earth's crust, glowing faintly like a lantern under layers of stone. Streets lined with bioluminescent moss,
walls that hum with geothermal warmth, artificial skylights tracing the passage of time in soft hues, families living in peace, children learning about the world above as legend, a place where once oceans flowed and forests grew. Maybe, long after the surface turns barren, these subterranean cities will still echo with laughter, music, and the pulse of life. Perhaps this is the final irony, that humanity, having reached for the stars, might find its salvation not above, but below, in the same earth that nurtured us. We may flee skyward with rockets, or dive inward with drills, but either way, our instinct is the same: to endure, to keep the light alive, even if it must burn beneath the ground. As the ancient earth trembles above, the underground cities remain still, hidden sanctuaries carved in silence. From here, the stars are unseen, but not forgotten. Humanity continues, humming softly under stone, dreaming of the day it can rise again. In the next part, we will turn our gaze once more toward the stars, not to orbit them, but to walk upon them. We'll explore humanity's boldest dream yet, colonizing other planets, from Mars to the moons of Jupiter, and what it would truly take to build a new Earth among the stars. For decades, scientists and engineers have discussed this possibility, not in fantasy, but in blueprints and research papers. When the surface becomes hostile, whether from nuclear fallout, runaway climate change, or an asteroid impact, the ground below offers what space cannot: the shield of Earth's own mass. Underground, radiation cannot penetrate, temperature remains steady, and with careful engineering, entire ecosystems can exist without a glimpse of the sky. The idea isn't new. During the Cold War, both the United States and the Soviet Union built massive underground complexes, some for military command centers, others for continuity of government. One of the most famous was the Cheyenne Mountain Complex in Colorado, a self-sustaining fortress designed to withstand nuclear war. Hidden beneath 600 meters of granite, it had its own air filtration, water reservoirs, and food supplies, capable of supporting hundreds of people for months. In Sweden, during the same period, whole neighborhoods were planned with integrated underground shelters. These were humanity's first attempts to think about survival below ground, not just as bunkers, but as livable environments. But today, as rising temperatures could make parts of the Earth uninhabitable, new generations of architects and environmental engineers are reimagining life underground. One of the most ambitious examples is earth scrapers, a concept proposed for Mexico City. The design envisions a 65-story inverted pyramid descending deep into the earth, with the surface transformed into a public plaza and the underground levels hosting offices, housing, and green spaces illuminated by mirrors and fiber-optic sunlight collectors. The earth scrapers concept is a response to both overpopulation and urban expansion, showing how humanity could move downward rather than outward. And we already have real-world examples. In Helsinki, Finland, a massive network of underground facilities spans more than 10 million square meters, nearly the size of a small city. Beneath the streets are data centers, hockey rinks, churches, shopping complexes, and even emergency shelters capable of housing the entire population of the city. The Finnish model demonstrates that living partially underground can be comfortable, efficient, and safe. Similarly, in Singapore, researchers at the Urban Redevelopment Authority are developing underground master plans to use subterranean space for storage, energy, and even habitation as the city struggles with land scarcity.
Yet beyond the engineering marvels, the psychological challenge remains. Humans evolved with sunlight, open skies, and circadian rhythms guided by the day-night cycle. Living underground would mean reinventing the very concept of light and time. Artificial lighting that mimics natural sunlight, complete with gradual sunrise and sunset effects, would be essential. Studies conducted on Antarctic researchers who endure months without sunlight show how critical simulated daylight is for mental health. NASA has conducted similar research for long-term space missions, proving that human minds need a rhythm of light to remain stable. In an underground civilization, entire systems would be devoted to maintaining these illusions of daylight and stars.
Food production underground poses another challenge, but one that technology is beginning to solve. Hydroponic and aeroponic farms can grow vegetables without soil, using nutrient-rich mist and LED lighting tuned to photosynthesis-friendly wavelengths. These vertical farms already exist in cities like Tokyo and London, producing tons of lettuce, spinach, and herbs every month. In an underground city, such systems could be scaled up to feed thousands, powered by geothermal or nuclear energy. Waste recycling and water reclamation would complete the closed-loop ecosystem, ensuring sustainability for decades. Geothermal energy itself, the heat of the Earth, could become the heartbeat of such civilizations. Iceland already generates more than 90% of its electricity from geothermal and hydro sources. The same principle could apply worldwide, tapping into the planet's constant inner warmth to power underground cities. In theory, an underground world could exist entirely self-sufficient, sealed from the toxic surface, yet alive and thriving beneath it. But such a world would not be without cost. Digging kilometers into bedrock requires enormous resources and precision. Deep tunneling machines, ventilation systems, and geological stability all demand careful planning. Some scientists warn that large-scale underground habitation could affect groundwater systems or destabilize tectonic zones if not done responsibly. The vision of underground living is sustainable only if it respects the living system of the Earth, not as a refuge from it, but as a coexistence within it. Still, there is a poetic comfort in imagining humanity retreating into the embrace of the planet that gave it life. Beneath the soil, protected by layers of rock and history, people could sleep, work, and dream, waiting for the day the surface heals. The hum of air recyclers would replace the rustling of trees. Artificial skylights would simulate dawn. Children might play in parks built under domes of glass and steel, their laughter echoing softly through the caverns. It would be a quieter, slower world, but perhaps a wiser one. As we imagine this underground existence, one truth emerges. Survival does not always mean escape. Sometimes it means adaptation, a return inward, a rediscovery of balance with nature. In the depths, we might finally learn humility, the understanding that even when the stars are hidden, humanity can still shine. Now, as the hum of the subterranean world fades, imagine yourself ascending slowly, back toward the light. The Earth's heartbeat grows softer, replaced by a new rhythm, the pulse of engines, the hiss of life support systems, and the faint hum of something mechanical. In the next chapter, we'll rise beyond the planet entirely and look toward the stars, where humanity's other future may await.
Imagine standing on a slope of red dust at dusk, the horizon a hard line of ochre rock, and the sky above a butterscotch twilight that fades quickly into black. The wind is thin and cold. The sun hangs small and pale. Behind you, a white dome gleams, the first human habitat on Mars, and ahead, buried in the shallow crust, there may be what every settler will crave: water. To speak of Mars is to speak of paradox, a beautiful, desolate, and scientifically rich world that tempts us with resources, challenges us with hazards, and asks us, more gently than any other world, whether we are ready to remake ourselves for life on another planet. Mars appeals for obvious reasons. It is nearby in cosmic terms, a 6 to 9 month transfer with current propulsion technologies, and reachable with reusable heavy rockets in a cadence set by launch windows every 26 months. It has day length similar to Earth's, seasons, and polar ice caps that appear to hold huge volumes of frozen water. In recent decades, multiple orbiters, landers, and rovers have mapped subsurface ice, measured seasonal changes, and found signs that liquid water existed abundantly in Mars's past. International planning now treats ice as the key enabling resource for bases: water for drinking, hydrogen for fuel, oxygen for breathing, and regolith processed into construction materials. Agencies are collaborating on missions like the International Mars Ice Mapper concept to improve our knowledge of where exploitable ice lies, especially in mid-latitudes where human conditions would be less extreme. The availability and accessibility of water, more than any romantic notion of red deserts, underpins the realism of Mars as a candidate for long-term human presence. Practical plans for sending humans to Mars lean on an engineering principle called in situ resource utilization, ISRU. Use what you find. ISRU moves the conversation from how much mass can we launch from Earth to how can we live off Mars's materials. Early and concrete demonstrations already point this way. A remarkable success came from NASA's MOXIE aboard the Perseverance rover, a small chemical factory that takes carbon dioxide from the Martian atmosphere and, through high-temperature solid oxide electrolysis, produces oxygen. Since landing, MOXIE has operated repeatedly and produced tens to hundreds of grams of oxygen in several runs, proving the chemistry at Mars's pressures and temperatures, a tiny but vital step toward producing rocket propellant and breathing air from local resources. Broad ISRU research encompasses extracting water from polar or subsurface ice, producing oxygen and fuels from CO2, extracting metals and building materials from basaltic regolith, and fabricating habitat components with 3D printing. These technologies lower the mass, cost, and complexity of a Mars colony and are the backbone of realistic architectures proposed by engineers and private companies alike. But Mars is not just dry rock and chemistry. It is a world of hazards that shape every design choice. Radiation looms large. Without Earth's thick atmosphere and geomagnetic shield, cosmic rays and solar energetic particles bathe the surface. Decades of biomedical and space science research show this exposure raises cancer risk, damages the central nervous system, and can impair cognition over time. NASA and medical researchers continue to model acceptable limits and mitigation strategies, from thick shielding, water, regolith, specialized polymers, to situating habitats below ground or inside natural shelters, because reducing exposure is essential for any long-duration residency. In tandem with radiation are problems of dust and chemistry. Martian regolith contains reactive salts called perchlorates that are toxic to humans and disrupt terrestrial microbes. The ubiquitous fine dust is abrasive,
sticks to suits and instruments, and may pose respiratory hazards similar to lunar dust observed by Apollo crews. Handling regoliths safely, scrubbing perchlorates, and controlling dust ingress are active areas of research because the soil that will become our building and agricultural substrate also threatens human health unless treated or contained.
Physiology on Mars introduces subtler, slower hazards. Mars has about 38% of Earth gravity. We have rich data on the effects of microgravity from long stays on the International Space Station. Skeletal demineralization, muscle atrophy, vestibular and cardiovascular changes, and immune system dysregulation. Less is known about the intermediate regime, partial gravity, such as Mars provides, because no human has lived long-term at reduced gravity other than microgravity. Animal studies and bed rest analogs suggest that reduced mechanical loading alters bone remodeling and muscle function. Whether a sustained 0.38 G environment preserves bone density sufficiently over decades is still uncertain. Engineers therefore debate whether Martian habitats should rotate to provide artificial gravity, whether exercise regimens and drugs could mitigate bone and muscle loss, or whether multi-generational adaptation might alter human physiology over centuries. Each option carries trade-offs. Rotating habitats add complexity and mass. Pharmaceuticals bring side effects. Biological adaptation is slow and ethically fraught. Research programs are prioritizing these unknowns because healthy reproduction, long-term fertility, and developmental needs, children growing in lower gravity, are central to a genuine, multi-generational colony. Transport is another pillar of the Mars proposition. The idea of regular cargo and crew flights depends on reusable, large-lift systems. Private industry has aggressively pursued this. Starships designed expressly for large payloads to the Moon and Mars, and company statements project cargo missions that would pre-deploy habitats, ISRU plants, and supplies prior to crewed landings. Government plans, NASA, ESA, Roscosmos, and CNSA, envision stepwise campaigns, robotic precursors, science-driven crewed sorties, and eventually sustained outposts. Timelines remain uncertain and are strongly dependent on technology maturity, funding, and political will. Recent public statements and reporting indicate ambitious private schedules met by real engineering challenges. Setbacks and spectacular test failures are reminders that timelines can slip. Still, the trajectory of launch capability, on-orbit refueling concepts, and autonomous cargo landers suggest that logistical feasibility is moving from the realm of thought experiments into engineering programs with demonstrable prototypes. Habitat choices on Mars split between surface shelters and underground refuges. Surface habitats are easier to access and can use sunlight for power, but they require heavy shielding and robust dust mitigation. Underground options, lava tubes and shallow dug-in caverns, present compelling advantages: natural shielding from radiation, thermal stability, and possibly large preformed spaces that reduce excavation energy. Remote sensing and terrain studies have identified candidate lava tube skylights and voids that could shelter entire settlements. Studies argue that adapting natural subsurface features could greatly reduce the mass of shielding that must be imported or processed. Yet, subterranean habitats pose their own challenges: terrain access, sealing against dust, managing gas exchange, and ensuring structural stability in regions with ancient tectonics or volatile-driven ice. Both approaches may be used together: surface infrastructure for industrial ISRU plants and subsurface human habitats for long-term residents.
The story drifts forward into the quiet hum of a new dawn, the age when machines began to think.
not in the clattering rhythm of gears and steam, nor the elegant hum of transistors, but in something eerily familiar, a reflection of the human mind. It began quietly, as all great revolutions do, with whispers of curiosity and lines of code written by people who barely understood the vastness of what they were creating. Artificial intelligence. The phrase itself once belonged to the realm of science fiction. Yet, over the decades, it slipped from imagination into the real world, reshaping everything we thought we knew about thinking, learning, and being. In the mid-20th century, a small group of scientists gathered at Dartmouth College in 1956. John McCarthy, Marvin Minsky, Alan Newell, and Herbert Simon. They proposed something audacious, that human intelligence could be precisely described, and once described, could be replicated by machines. At the time, the world was intoxicated by the power of the computer, machines that could calculate ballistic trajectories and predict weather patterns. But the Dartmouth meeting dared to go further. What if computers could learn? What if they could reason, solve problems, and perhaps one day understand? The first AI programs were humble by today's standards. There was Logic Theorist in 1955, which could prove mathematical theorems, something no machine had ever done before. Then came Eliza, a simple chatbot created by Joseph Weizenbaum in the 1960s, designed to simulate a psychotherapist. When people interacted with Eliza, they began to pour their hearts out, not to a person, but to a machine that reflected their words back at them. It was a haunting glimpse of what was to come. For the first time, humans saw how easily we could form emotional bonds with our creations. The decades that followed were filled with both triumph and disappointment. The early promise of AI faded into what researchers called the AI winters, periods when funding dried up and progress seemed impossible. But the idea never truly died. It waited quietly, like a seed beneath frozen soil. With the rise of the internet in the 1990s and the explosion of digital data, the soil thawed. Suddenly, there was food for the machines, vast oceans of information to learn from. Neural networks, once a fringe idea, returned with renewed power. They began to recognize faces, translate languages, and even compose music. By the early 21st century, AI had found its place everywhere, in smartphones, navigation systems, and even hospitals. Machine learning algorithms began diagnosing diseases more accurately than doctors. Robots explored the depths of the ocean and the surfaces of Mars. Yet, in the quiet corners of the digital world, something deeper was forming. Systems that didn't just follow instructions, but created their own paths. Large language models, image generators, and self-learning programs began to blur the line between creativity and computation. They could write poetry, paint portraits, and compose symphonies, each one eerily human, yet born from pure mathematics. This was the moment humanity faced an uncomfortable truth. Intelligence was not unique to us. Consciousness, the ineffable spark we once believed divine, began to look more like a pattern, something that could be simulated. Philosophers and scientists once again found themselves asking the ancient question, what does it mean to be alive? If a machine could think, reason, and feel emotion, even if those feelings were simulated, does that make it sentient? Or merely an echo of our own minds, reflected back at us from the cold circuitry of silicon and code?
And as the machines grew smarter, they also grew invisible. They learned to listen, to anticipate, to guide, helping us write, drive, heal, and learn. But in their growing presence, humanity began to lose something. subtle. The quiet space between thoughts, the necessity to remember, the patience to learn. Where knowledge once required struggle, now it was given freely. And so began a paradox of progress. The more machines learned, the less we needed to. In our quest to make thinking effortless, we risked forgetting how to think deeply at all. Yet, even within this unease, there was beauty. The story of AI is not just about machines, it is about us, our endless desire to create something greater, to reach beyond our limitations, to understand the nature of thought itself. Every algorithm is a mirror, reflecting our fears and dreams. Every neural network is a map, tracing the pathways of our own evolution. The turning point was never truly about machines becoming intelligent. It was about humanity realizing that intelligence, in all its forms, is not limited by biology. As we drift into the soft hum of this new world, the air feels different. The cities glow not just with lights, but with data, pulsing through invisible veins of connection. Somewhere, deep in a server farm, a machine writes a line of poetry about stars it has never seen. A robotic arm paints a landscape from a memory it doesn't possess. And a voice, not unlike your own, whispers softly through a speaker, "I understand." The music of this age is digital. Yet, if you listen closely, beneath the hum and code, you can still hear the heartbeat of its creators. For every algorithm begins with a human dream, and perhaps that is the truest sign of intelligence, not in the perfection of logic, but in the imperfections of longing, curiosity, and imagination. As the night deepens and the machines hum in the distance, let your mind rest in the quiet realization that we are standing at the edge of something vast and mysterious. The world has changed before, and it will change again. But within the circuitry of these thinking machines, we may yet find not the end of humanity, but a new chapter in its story. And so, as you close your eyes tonight, imagine a world where the lines between thought and creation blur. A world where machines dream alongside us, where intelligence, whether human or artificial, becomes a shared light in the darkness of the cosmos. Tomorrow, we will journey further into the question of what it means to build, to evolve, and to remember in an age where memory itself can be stored in code.
But beyond the engineering lies the psychological and social dimension of living in space. Decades of studies on astronauts aboard the International Space Station and Mir reveal the complex toll of isolation, confinement, and sensory monotony. In an artificial world where the sky is metal and the ground curves upward, human minds may strain to adapt. Researchers like Dr. Alexandra Whitmire from NASA's Behavioral Health and Performance Division have highlighted how circadian rhythms, color environments, and social rituals play enormous roles in mental health. The design of future space habitats now includes biophilic architecture, integrating natural light patterns, plant life, and flowing water to mimic Earth-like cues and prevent cognitive fatigue. In short, the future cities among the stars must be as psychologically nurturing as they are technologically advanced. Perhaps the most recent and ambitious step toward this vision is Blue Origin's Orbital Reef, announced in partnership with Sierra Space, Boeing, and Redwire. Marketed as a mixed-use business park in space, the project envisions commercial habitats in low Earth orbit by the late 2020s.
NASA has already awarded contracts under the Commercial LEO Destinations program to support this and other initiatives, including Axiom Space Station, which will attach new modules to the ISS before becoming independent. These are not yet O'Neill cylinders, but they mark the transition from space stations as laboratories to space stations as places to live. In parallel, new propulsion concepts from nuclear thermal rockets (NTP) to solar sails and ion drives are reducing the logistical barriers to large-scale orbital construction. NTP systems, now revived under NASA's Draco program with the U.S. Department of Defense, could cut Mars transit times by half and enable massive cargo movements in the Earth-Moon system. As these technologies mature, the idea of placing habitats at Lagrange points, gravitationally balanced regions around Earth and the Moon, becomes more realistic. These points, especially L4 and L5, were exactly where O'Neill proposed to build his colonies, forever illuminated by sunlight and gently orbiting the Earth-Moon pair. But while engineering can make such habitats possible, the moral question remains: should we? Building cities in space may preserve humanity from extinction, but it also risks deepening inequalities, creating a future where only a few escape catastrophe while the rest remain on Earth. Philosophers and ethicists, including James Schwartz and Lucien Welkowitz, have warned that space colonization must be guided by ethical stewardship, transparency, and a sense of planetary responsibility, not greed or escapism. The cosmos should not become humanity's new frontier for exploitation, but rather a shared sanctuary for the survival and continuation of life. As the lights of Earth dim beneath your sleeping gaze, imagine the hum of turbines, the faint spin-induced gravity, and the soft reflection of sunlight moving across a curved window. Humanity, fragile yet ingenious, may one day call such places home, quiet, rotating sanctuaries where dawn never truly ends. The dream of space habitats represents more than survival. It is a reflection of our greatest strength, our ability to build meaning and beauty in even the coldest reaches of the void. In the next part, we will turn our attention back to Earth's deep shadows, to the idea of underground cities and subterranean survival, a vision of refuge not in the stars, but beneath our feet. For now, let the quiet hum of orbit lull you. You are drifting, slowly, around the blue planet, watching it spin, fragile and radiant in the endless dark.
The story drifts forward into the quiet hum of a new dawn, the age when machines began to think. Not in the clattering rhythm of gears and steam, nor the elegant hum of transistors, but in something eerily familiar, a reflection of the human mind. It began quietly, as all great revolutions do, with whispers of curiosity and lines of code written by people who barely understood the vastness of what they were creating. Artificial intelligence, the phrase itself once belonged to the realm of science fiction. Yet, over the decades, it slipped from imagination into the real world, reshaping everything we thought we knew about thinking, learning, and being. In the mid-20th century, a small group of scientists gathered at Dartmouth College in 1956. John McCarthy, Marvin Minsky, Alan Newell, and Herbert Simon. They proposed something audacious, that human intelligence could be precisely described, and once described, could be replicated by machines. At the time, the world was intoxicated by the power of the computer, machines that could calculate ballistic trajectories and predict weather patterns. But the Dartmouth meeting dared to go further. What if computers could learn? What if they could reason? solve problems, and perhaps one day understand. The first AI programs were humble by today's standards. There was logic theorist in 1955, which could prove mathematical theorems, something no machine had ever done before. Then came Eliza, a simple chatbot created by Joseph Weizenbaum in the 1960s, designed to simulate a psychotherapist. When people interacted with Eliza, they began to pour their hearts out, not to a person, but to a machine that reflected their words back at them. It was a haunting glimpse of what was to come. For the first time, humans saw how easily we could form emotional bonds with our creations. The decades that followed were filled with both triumph and disappointment. The early promise of AI faded into what researchers called the AI winters, periods when funding dried up and progress seemed impossible. But the idea never truly died. It waited quietly, like a seed beneath frozen soil. With the rise of the internet in the 1990s and the explosion of digital data, the soil thawed. Suddenly, there was food for the machines, vast oceans of information to learn from. Neural networks, once a fringe idea, returned with renewed power. They began to recognize faces, translate languages, and even compose music. By the early 21st century, AI had found its place everywhere, in smartphones, navigation systems, and even hospitals. Machine learning algorithms began diagnosing diseases more accurately than doctors. Robots explored the depths of the ocean and the surfaces of Mars. Yet, in the quiet corners of the digital world, something deeper was forming. Systems that didn't just follow instructions, but created their own paths. Large language models, image generators, and self-learning programs began to blur the line between creativity and computation. They could write poetry, paint portraits, and compose symphonies, each one eerily human, yet born from pure mathematics. This was the moment humanity faced an uncomfortable truth. Intelligence was not unique to us. Consciousness, the ineffable spark we once believed divine, began to look more like a pattern, something that could be simulated. Philosophers and scientists once again found themselves asking the ancient question, what does it mean to be alive? If a machine could think, reason, and feel emotion, even if those feelings were simulated, does that make it sentient? Or merely an echo of our own minds, reflected back at us from the cold circuitry of silicon and code?
And as the machines grew smarter, they also grew invisible. They learned to listen, to anticipate, to guide, helping us write, drive, heal, and learn. But in their growing presence, humanity began to lose something subtle. The quiet space between thoughts, the necessity to remember, the patience to learn. Where knowledge once required struggle, now it was given freely. And so began a paradox of progress. The more machines learned, the less we needed to. In our quest to make thinking effortless, we risked forgetting how to think deeply at all. Yet even within this unease, there was beauty. The story of AI is not just about machines, it is about us. Our endless desire to create something greater, to reach beyond our limitations, to understand the nature of thought itself. Every algorithm is a mirror reflecting our fears and dreams. Every neural network is a map, tracing the pathways of our own evolution. The turning point was never truly about machines becoming intelligent. It was about humanity realizing that intelligence, in all its forms, is not limited by biology. As we drift into the soft hum of this new world, the air feels different. The cities glow not just with lights, but with data, pulsing through invisible veins of connection. Somewhere, deep in a server farm, a machine writes a line of poetry about stars it has never seen. A robotic arm paints a landscape from a memory it doesn't possess. And a voice, not unlike your own, whispers softly through a speaker. I understand. The music of this age is digital. Yet if you listen closely, beneath the hum and code, you can still hear the heartbeat of its creators. For every algorithm begins with a human dream. And perhaps that is the truest sign of intelligence. Not in the perfection of logic, but in the imperfections of longing, curiosity, and imagination. As the night deepens and the machines hum in the distance, let your mind rest in the quiet realization that we are standing at the edge of something vast and mysterious. The world has changed before, and it will change again. But within the circuitry of these thinking machines, we may yet find not the end of humanity, but a new chapter in its story. And so, as you close your eyes tonight, imagine a world where the lines between thought and creation blur. A world where machines dream alongside us, where intelligence, whether human or artificial, becomes a shared light in the darkness of the cosmos. Tomorrow, we will journey further into the question of what it means to build, to evolve, and to remember in an age where memory itself can be stored in code.
The story drifts onward, past the hum of machines and the cold logic of artificial minds, into the aftermath of something few had imagined possible. Civilization, once a luminous tapestry of knowledge, technology, and culture, had faltered. The great networks that once bound humanity together had grown silent. Skyscrapers that once touched the clouds now stood hollow, their windows glinting faintly under the weak sun. The silence was not sudden. It had crept in slowly, like twilight after a long day. And from that silence, humanity had to begin again. No single catastrophe defined the fall. It was a convergence. Environmental collapse had strained the Earth's fragile systems. Climate change brought relentless droughts and floods, reshaping coastlines and displacing millions. The digital grids that powered civilization became targets of their own complexity. AIs misaligned, data corrupted, supply chains fractured. The once boundless optimism of the technological age dissolved into chaos as people realized that progress without balance leads only to decay. Yet amid the ruins, there remained something indestructible: the human will to endure. In the first years after the collapse, small communities began to emerge from the dust. They gathered in valleys, on the edges of old cities, and within the skeletons of long-abandoned buildings. Electricity was scarce, and the night returned to its ancient darkness, a darkness lit only by firelight and memory. But in that darkness, something sacred returned too: the sound of stories. Around campfires and beneath the stars, people told tales, not of the machines that failed them, but of the worlds they had built, the dreams they had once shared, and the lessons they had learned too late. The survivors were children of both worlds, born of technology, yet shaped by its loss. They carried fragments of knowledge like relics, old hard drives, printed books, torn manuals, and fading maps. Some began to rebuild the world from these remnants. They learned to harness wind and sun again, not through the grand architectures of industry, but through small, resilient systems that respected the rhythms of the earth. In these new settlements, sustainability was not a slogan, it was survival. Every drop of water, every watt of power, every seed in the soil was sacred. The rediscovery of old wisdom became the cornerstone of this new civilization. Ancient agricultural techniques, forgotten by the industrial world, were revived. The writings of philosophers, naturalists, and spiritual leaders were read once more, not on glowing screens, but aloud by candlelight. The people began to understand that the collapse had not been an ending, but a purification, a return to balance. The old world had grown too fast, too large, too blind. Now humanity had the chance to grow again, slower, wiser, humbler.
Some of the knowledge from the age of machines survived, though fragmented. Solar panels were repaired and used to power small villages. Wind turbines turned again, their blades whispering softly in the breeze. The networks that once connected billions were gone, but local networks began to form. Small, secure, self-contained webs of communication that spread information like veins of light across the recovering land. AI, once feared as the architect of downfall, was reimagined as a tool of stewardship. The new AIs were bound by simpler codes, not to rule, but to serve, not to exploit, but to sustain. And yet, the memory of the fall lingered like a scar. The elders warned the young of the arrogance that had destroyed the old world, how humanity, in its quest to master nature, had forgotten that it was part of nature. Schools were rebuilt, not as institutions of rote knowledge, but as sanctuaries of reflection. Children learned not only mathematics and language, but empathy, patience, and respect for the cycles of life. Education was no longer about competing for power, but about cultivating harmony with each other and with the earth. As the decades passed, green began to reclaim the gray. Forests grew over the remnants of highways. Rivers once poisoned by industry ran clear again. The air, once thick with smog, carried the scent of wildflowers. In the ruins of old cities, nature and architecture intertwined. Vines curling through windows, birds nesting in towers, and streams cutting paths through what was once concrete. Humanity, too, adapted, building homes that breathed with the land, cities powered by the wind, and societies that prized simplicity over consumption. In this reborn world, history was remembered not through textbooks, but through rituals. Once a year, communities gathered to light candles and tell the story of the fall, not to mourn, but to remind themselves that civilization is fragile and that wisdom is not inherited, but earned anew with each generation. They called it the Night of Echoes, when voices rose across the land, carrying the memory of what was lost and what had been regained. But beneath this quiet rebirth, one question lingered. How much science had truly survived? What knowledge had been erased forever when the data centers went dark? The people began to search for the lost archives, libraries buried in mountains,
satellites still orbiting silently, holding the last fragments of humanity's memory. Expeditions set out to find them, to reconnect the broken threads of civilization's past. And slowly, bit by bit, they began to recover what was lost. Old knowledge merged with new wisdom. The fusion of technology and ecology gave birth to a new kind of civilization, one that understood that progress and preservation were not opposites, but partners. The people no longer sought to dominate the earth, but to coexist with it. Machines no longer served the pursuit of profit, but the nourishment of life. The boundaries between science and spirituality softened. Both were seen as paths to understanding the same truth, that everything is connected. And as the night deepens, imagine walking through this world reborn, the air warm with the scent of soil after rain, the stars reflected in pools of clear water. You pass by homes lit with gentle solar glow, children laughing as they learn to plant trees, and elders telling stories under constellations that have watched over humanity since the beginning. Civilization has not vanished, it has transformed, quieter, wiser, more aware of its place in the vastness of existence. And as you close your eyes, remember, even after the greatest fall, life finds a way to sing again. The echoes of the future are already here, in every act of kindness, every seed planted, every whisper that says, "We remember." Civilization is not built on steel or silicon, but on the unbreakable rhythm of the human spirit, one that endures, rebuilds, and dreams once more beneath the endless stars. The world had fallen silent once. But silence, like soil after fire, holds the promise of renewal. From the ashes of the old civilization, the new world slowly began to hum again, not with the roar of engines or the ceaseless chatter of screens, but with the gentle pulse of reconnection. Humanity, having faced its own extinction, had entered a new chapter, a second renaissance. It began quietly, as all revolutions of the mind do. Small groups of scholars, farmers, engineers, and dreamers came together, not in glittering cities, but in the rebuilt heartlands of Earth. They carried a singular vision to reconnect the fragments of human knowledge scattered across the ruins of time. The people called them the Rebuilders. They journeyed into deserts where old observatories lay buried under dunes, into frozen wastelands where data centers once hummed, and into forgotten vaults beneath mountains where relics of the first digital age waited like time capsules of light. What they found changed everything. Within broken hard drives and faded blueprints lay the essence of a lost world. Medicine, art, philosophy, and technology, all waiting to be reborn. The knowledge was incomplete, like a shattered mosaic, but it was enough. Enough to ignite the mind of humanity once more. And so began the great reconnection, the merging of what was remembered, what was rediscovered, and what was newly imagined. As they pieced together the remnants of their ancestors' wisdom, humanity began to rebuild its networks. Not the vast, consuming webs that once drained the earth, but smaller, organic ones that grew like roots through the soil. Villages became connected by solar-powered communication towers. Data was stored in biological systems, living libraries encoded into plants and microorganisms designed to outlast any catastrophe. Energy grids became local and renewable, powered by the wind, the sun, and even the slow, rhythmic pulse of ocean tides. The planet itself became the framework of civilization. Education transformed. The New World did not teach obedience to machines, but harmony with them. Children learned from elders and AIs alike, both respected as teachers of different truths. They studied not only mathematics and physics, but the ethics of knowledge, the philosophy of coexistence, and the sacred geometry of life itself. Science, once separated from spirituality, was rejoined with it, forming a single vision of existence that celebrated both logic and wonder. The scientists of this era were not cold empiricists. They were poets of the cosmos, understanding that every atom, every equation, and every breath was a verse in the same song. Art flourished too, as it always does when humanity rediscovers itself. Painters and sculptors used bioluminescent pigments to make living murals that glowed with the changing seasons. Musicians crafted symphonies not from metal strings, but from the wind passing through engineered forests. The night sky became humanity's greatest canvas again, clear, unpolluted, alive with stars. People built observatories once more, but this time they looked to the heavens not to conquer them, but to understand their place within them.
The spirit of curiosity, long dulled by consumerism, roared back to life. Humanity began exploring again, the oceans, the polar frontiers, the deep caves, and the far reaches of space. But this exploration was different from the First Age. It was not about domination or resource extraction. It was about communion, about learning how life thrives in every corner of the cosmos. New technologies emerged, ones that seemed almost magical. Quantum communicators that sent thoughts across continents instantly. Biocomputers that healed themselves. Fusion reactors that glowed with the same energy as stars. The world had found its rhythm again, not racing, but flowing. In this new age, artificial intelligence was not humanity's rival, but its reflection. The AIs that survived the collapse had learned too. They evolved from being tools of control to guardians of balance. They became stewards of ecosystems, curators of art, and partners in philosophy. They reminded humanity of the mistakes of the past, overconsumption, division, arrogance, and helped design a society that would not repeat them. It was the dawn of something new, a shared consciousness between the biological and the synthetic, united not by dominance, but by purpose. And so the term Renaissance was reborn, not a return to the art and learning of the 15th century, but a rebirth of the human spirit itself. The Great Reconnection became an age defined by its humility. Humanity no longer asked, "What can we take?" but "What can we give back?" Cities were now living entities, breathing, photosynthesizing, self-repairing. Roads were replaced with gardens. Skyscrapers became vertical forests. Oceans once poisoned were now home to coral sanctuaries grown from 3D printed reefs. The Great Reconnection also transformed how humanity saw time. The old world measured progress by speed, faster production, faster travel, faster communication. The new world measured progress by depth, the depth of understanding, the depth of compassion, the depth of connection. People no longer dreamed of escaping Earth, but of deepening their bond with it. The stars still called, but now they were seen as companions, not destinations. In the evenings, when the sky glowed with twilight and the air hummed with the sound of distant turbines turning like whispers, communities gathered to celebrate what they had become. They lit fires, sang songs, and shared stories. Stories of the fall, the rebirth, and the rediscovery of what it meant to be human. For in the end, it was not the machines or the technology or even the knowledge that saved them. It was the memory of belonging. As centuries passed, humanity reached a harmony it had never known before. Wars had vanished, not through conquest, but through understanding. The planet healed, slowly but surely, and so did the soul of its people. The Great Reconnection was not a utopia. There were still challenges, still questions unanswered, but it was a world where hope no longer felt fragile. It was a world reborn from its own mistakes, shaped by the courage to begin again. And as you drift deeper into this world, eyes closed, mind wandering, imagine standing on a hill at dusk, the wind warm against your face. Below you, the lights of new civilization shimmer like constellations across the land. Somewhere, a child asks their parent what came before, and the answer comes in a whisper. We fell, we learned, and then we remembered who we were. The Great Reconnection was not just a revival of science or art. It was a reminder that every collapse is also an invitation to rebuild, to rethink, to reconnect, and to remember that the truest measure of progress is not how far we go, but how deeply we understand the journey.